Finish off the PowerPoint slides for this chapter, we're going to talk about a property called inductance. Now, previously we talked about capacitors, and a capacitor is characterized by a property called capacitance, which is measured in farad. And we talked about resistors, and we said resistors are characterized by a property called resistance, which is measured in ohms. An inductor is a device we have been working with, although we didn't formally introduce it. One common example of an inductor is a solenoid. And inductors, such as solenoids, are characterized by a property called inductance. So, to motivate the idea of inductors and inductance, let's take two coils of wire. So we could think of this as being two solenoids, and we're going to set these coils to be fairly close together. So these two coils, we have a left coil and a right coil. They're not directly connected by a wire, so they are separated from each other, but they are close enough together that they can interact. And specifically, what we're going to be interested in is if one coil carries a current, that coil will create a magnetic field because this is a solenoid that has a magnetic field when a current flows around it. And that magnetic field will stretch out of the solenoid and wrap around. And then this coil on the right is close enough to see that magnetic field. And so what we're going to be interested in is the EMF induced in the right coil due to a changing magnetic flux in the left coil. So we could say, okay, how much EMF, how much voltage will be induced in the right coil? Well, that depends on the number of loops, the rate of change of magnetic flux with respect to time. This is the equation for Faraday's law that we had just given previously. So the amount of EMF, the amount of voltage that is induced on this coil on the right, depends on the details of the scenario. How tightly packed are the coils? How strong is the current flowing through the coils on the left? Because the stronger the current, the greater the magnetic field. And as the current changes, the magnetic field will change, which will imply the magnetic flux at the location of the right coil will change. And if the coils are close together or far apart, that will matter. So the specific numerical details of the scenario depend on what's going on. We're not going to worry about that. Let's just worry about the big picture where a changing current, a change will imply a changing magnetic field or a changing magnetic flux. And then this coil on the right will see that changing magnetic flux and a voltage will be induced. So, as I said before, a changing magnetic field will induce a voltage, and the source of the magnetic field around this coil on the right is because the current through these coils is changing. So instead of thinking of this as a changing magnetic flux, I could in a way think of the voltage on the coil on the right is due to a changing current in the coil on the left. Because remember, voltage, current, magnetic field, all these ideas are very closely intertwined with each other. So if I want, I could say the voltage induced is N rate of change of magnetic flux, but I could just as well write that the voltage induced in this coil on the right is the rate of change of the current on the left multiplied by something, and this term M is a term that is just based on the details of the scenario. So I'm intentionally being vague right now as to what is the nature of this term M, but what I'm trying to say is I could think of the voltage in the coil on the right being the result of a changing flux. Well, a changing flux is due to a changing magnetic field in this case, and a changing magnetic field is due to a changing current in the coil on the left. So I could just as well say the amount of voltage induced in the coil on the right is due to the changing current in the coil on the left. Now, I don't even need a second coil on the right, because if I have a changing magnetic flux through this coil, there will be an induced EMF in this same coil. And this induced EMF will imply the existence of an induced current. So similar to the previous slide, I could think about the induced EMF in the coil as due to a changing magnetic flux through the coil, or I could think about the induced voltage, the induced EMF through this coil is due to the rate of change of the current in this coil. So I could say that the induced EMF in the coil that I have here is the rate of change of current multiplied by this term L. And L is, again, a term based on things. So L, we will see in an example problem very soon, depends on what type of inductor I am working with. So I told you that a common example of an inductor is a solenoid, but there are other types of inductors. A toroid, which is basically a solenoid wrapped into the shape of a donut. A toroid is a different type of inductor. Now, remember Lenz's law. Nature is going to oppose a change in magnetic flux. So when I am talking about self-inductance, I could talk about the induced voltage is given by this equation, or I could talk about the induced voltage in this coil is given by this equation. Both of these equations for self-induced voltage are perfectly valid. In practice, though, we're going to see through example problems that this equation will be more useful when we're trying to solve things. Now, comparing these two equations, I could learn something about what is this constant L. We have a number of coils. We have a change in magnetic flux with respect to changing current. But this term here doesn't really tell me anything about what L really is. It doesn't help give me a good visualization of what L is. So we're going to demonstrate what do we mean by self-inductance through an example problem. And when you're working with inductance problems, the unit of inductance is the Henry. So we talk a lot about induced current, but what's an effective way to think about induced current? Now, this discussion I'm going to have, it's not physically accurate on a fundamental level. This is not exactly how nature works, but in my opinion, this could be a useful thought experiment to have in our mind when we're thinking about induced current. So let's say I have a wire, and let's say this wire carries a current of 4 amps. So here's my original current of 4 amps. Now, I drew this as 4 amps flowing to the right. A current is just made up of many charges, more or less all moving in the same direction. Let's imagine somehow we were able to set up a scenario where we have a second current also flowing through the wire. The second current will not affect the motion of the first current. Let's suppose we have a second current that is 1/2 amp flowing to the left. Well, if I combine the effect of both of these currents together, I have 4 amps flowing to the right, I have 1/2 amp flowing to the left. So I could kind of think of this as like I total is 3.5 amp to the right. Now, this is not really how nature works, because if you think about what is a current, well, electric field is created inside the wire. The electric field pushes the charges in a preferred direction. It's not like you have an electric field pointing to some charges only move to the right and other charges only move to the left. But for the purpose of how to think about induced current, this mental image could be instructive, where I think of my original current is going to be the 4 amps, and then I add in the effect of the induced current. So in this case, the induced current is flowing to the left in the opposite direction. So combining the effect of the original current with the induced current, my total current is 3.5 amps to the right. And again, like I try to emphasize in some of these lectures, induced current, induced magnetic field, these quantities are not necessarily always going to be in the opposite direction. Sometimes you could have a scenario where the induced current is going to be in the same direction as the original current. When that occurs, you would combine their effects. So in total, we would have, in this scenario, 4.5 amps of induced current. So let's think about, we're talking about inductance, and inductance is a property of a device called an inductor, and one example of an inductor is a solenoid. So we said before that the amount of induced voltage could be written as N, rate of change of magnetic flux with respect to time, or we could say that the amount of induced voltage could be written as this other term, L times delta I over delta T, rate of change of current with respect to time. Now, both of these equations are correct. We could say the induced voltage is this much. We could say the induced voltage is this much. They're both right. And if you think about it for a minute, well, what creates magnetic fields? Moving charges create magnetic fields. So if I have my magnetic field change, I'll have my flux change, and because I have a rate of change of flux, I create voltage. Well, because moving charges are the thing that create the magnetic field, I could say, how do I get my magnetic field to change? Well, I either turn up or turn down the current. So the rate of change of the current will be related to the rate of change of the magnetic field, which will be related to the rate of change of magnetic flux. So both of these equations are perfectly valid to use. Now, if I want, I could set them equal to each other. Maybe we could learn something about what is this new term L. N we defined before as the number of loops a wire. We talked about magnetic flux. We know what current is. What is this L? So I could set them equal to each other. So I get N is equal to rate of change of magnetic flux with respect to time. Oh. I say N times rate of change of magnetic flux, and I could say equal to L times rate of change of current with respect to time. Okay, we have a delta T in the top and bottom, so these could cancel out. I could do some algebra, solve for L, and I find L is equal to N, change in magnetic flux over change in I. Now, at this stage, I don't think this really gives us a good mental picture of what is this term L. So let's apply this specifically to the case of a solenoid. Like I said, a solenoid is the classic example of an inductor. So what we're going to do is we're going to ask, what is the inductance of a solenoid? What is the inductance of a solenoid? Now, basically we are asking, what is L equal to for a solenoid? Before, to make an analogy, when we were talking about resistors, we said the resistance of a resistor is rho L over A. We're trying to find a similar equation where for a solenoid, I could say L is equal to, I will have some stuff for a solenoid here. So to make an analogy, we're doing this, but for a solenoid. So I will write this equation right up here to make space. L equals N change in magnetic flux over change in current. Now, a solenoid, as we said before, is just a coil of wires wrapped in the shape of a cylinder. So I'll draw my solenoid. So here's my solenoid with all the coils of wire. And when I send electrical current through the solenoid, the electrical current will go around the solenoid and create a magnetic field through the center of the solenoid. So I send electrical current this way through the solenoid. Here is my I. And by sending the electrical current through the solenoid, I could use the right-hand rule. In between the solenoid and myself, the current is flowing upward. The curly part is my four fingers. My thumb points to the left. So the magnetic field inside the solenoid will point to the left. So here's my magnetic field B. Okay. What I'm going to do is N is the number of loops in my solenoid, the number of loops a wire. We have a rate of a change in magnetic flux. We have a change in current. So let's assume that initially I is equal to 0, and initially the current, I'll write that as I initial. If the current inside a solenoid is 0, then the magnetic field will be 0. So that implies that B initial is 0. Now, let's assume at some time later the current went from 0 to something bigger than 0. So I'll say at the final moment, I final. I'm going to just write that as being equal to I as the current itself. So I go from current of 0 to current of I. Now, we learned that before, the strength of the magnetic field in a solenoid is equal to mu naught N over L times I, where N is the total number of loops of the solenoid, and L, cursive L, is the length of the solenoid. So here, N equals total number of loops. L is equal to the length. And sometimes this is also written as mu naught N times I. Here, lowercase n is just the number of loops per unit length. So both of these equations are written and are reasonably common to see. I'm going to use this equation for my B final. So I could write B final, in this case, is going to be B final is equal to mu naught times big N divided by the length of the solenoid times I. Okay, what is the change in magnetic flux? Well, to find the change in magnetic flux for the solenoid, I'm just going to, flux is going to be magnetic field times area, because the surface area of the loops never changes, so the surface area is going to be constant. The strength of the magnetic field is what's going to be changing. So I could say that phi B initial is equal to B, which is 0, times the cross-sectional area of the solenoid, which is A, which is just going to be 0. Phi B final is just going to be the final magnetic field, which was this term here, mu naught big N over L times I, times the cross-sectional area of the solenoid. So here, solenoid has cross-sectional area A. Okay, we have a bunch of terms. The current initially is 0, which implies the magnetic field is 0, which implies the magnetic flux through the solenoid is 0. Later on, the current has a magnitude of I. That implies there is some magnetic field, this much, depending on the details of how long the solenoid is, how many loops, and so on. And the magnetic flux is going to be B times A. The magnetic field is down the length of the solenoid, so that angular term, cosine of theta, just becomes the number 1. So we have B times A times cosine of 0, which is 1. So I could say, if I plug these values in over here, the inductance of a solenoid could be written as N times the change in magnetic flux, so final minus initial, mu naught times N over L times I times A minus 0, final minus initial, divided by the change in current. So that would be final current, we said is I, initial current is 0. Now at this point, I'm just going to solve some algebra and rearrange. So I could say L is equal to N times mu naught big N over L I A divided by I. So I look at this, I see the current and the current cancel, and then I could write L is equal to, I'm just going to rearrange some of the algebra. I'll put mu naught first, then I'll write N squared over L times A. So what do we have here? Well, mu naught is a fundamental constant of nature. So mu naught is just kind of like epsilon naught for electric problems. Mu naught is one of the magnetic constants of nature. We said N is the total number of loops L is the length, which will be measured in meters. A is the cross-sectional area. Which will be measured in meters square. Now let's think about this result we have. So for this result, if I went to build a solenoid, so I go to a machine shop, I would take some wire, I would wrap it around a cylinder, and I would have my solenoid. Some things that would be under my control. I could choose how big is the cylinder that I wrap around. Is it really thin like a strand of spaghetti, or is it thick like a poster tube? How many loops of wire, do I pack the wire really close together, or do I spread the wires out? Do I have many loops and a really long solenoid, or do I just have a really short solenoid? All of these three terms are under my control. When I build my solenoid, I could choose the value of these terms. So I have some combination of these terms that are under my control multiplied by a constant of nature. When I did this is kind of like, what if I wanted to go to a machine shop and build a resistor? Well, to build a resistor of resistance R, I would choose what material I build my resistor out of. So that would basically say I choose what row is. I would choose how long my resistor is going to be. I would choose my cross-sectional area of my resistor. So I combine these terms, I get something measured in ohms. I combine these terms, I get something measured in henries. So the resistance of a resistor is given by this equation. The inductance of an inductor when we're talking about solenoid is given by that equation. So the last thing I'll say is sometimes, like we said before, little n is equal to big N over L. So I could just make a substitution that implies n squared is equal to big N squared over L squared. So that implies n squared times L is equal to big N squared over L. So if I want, I could just as correctly say the inductance of a solenoid is equal to mu naught times n squared LA. And this also would be correct. I think more often than not, you're going to be using that equation for the inductance of a solenoid. By more often than not, though, I mean like 80% of the time versus 20% of the time. So it's in the majority, but it's not an overwhelming majority. So what would a problem with an inductor and a solenoid inductor actually look like? So in a way, I could kind of think of the inductance as saying, if I change the current in a solenoid, how much EMF will I induce? So let's just leave that up. And what we have is we have now for the final example problem in this chapter, a 500 turn solenoid is 8 centimeters long. A current is increased from 0 to 2.5 amp in 0.35 seconds, and an EMF of 0.012 volts is induced. What are the inductance and cross-sectional area of the solenoid? So we have, for this question, the induced voltage is equal to L times the rate of change of the current flowing through the solenoid. So, okay, I could plug some numbers in, and I find we had a induced EMF of 0.012 is equal to L. Now, the current initially was 0, then it became 2.5. So delta I is equal to 2.5 minus 0. And this occurred over a time scale of 0.35 seconds. So delta T is 0.35 minus 0. So then I have 2.5 over 0.35. So if I run some algebra through, I get the inductance of the solenoid is 1.7 times 10 to the minus 3. And the unit of inductance is the Henry with capital H. The second part of this problem asks what is the cross-sectional area of the solenoid. So, okay, for a solenoid we have this equation. So I could plug numbers in. L is equal to 1.7 times 10 to the minus 3. Mu naught is 4 pi times 10 to the minus 7. Then I have n squared over L. So we have a solenoid with 500 turns or 500 loops. And the solenoid has a length of 8 centimeters. We always want to work in meters, 0.08 meters, and times the cross-sectional area. All I'm doing is I'm plugging terms now into this equation to get this line. So L mu naught, n squared, cursive L, A. And then I could solve for A, and I get the cross-sectional area of the solenoid is 4.3 times 10 to the minus 4 meters squared. So, like I said, a solenoid, the inductance of a solenoid, you could think of that as if I change the current in a solenoid from an initial to a final value, do I induce a lot of voltage or do I only induce a little bit of voltage? I'm just using this equation right here. So given some amount of change in current, how much voltage do I induce? And L is a measure of, or in a way I could think of L determines how much voltage I induce given a certain change in current.